Welcome everyone for the Physics Department Special Colloquium. So I was supposed to introduce Professor D.D. Sharma, but it is first of all not required, but if it has to be done, it can become another talk. So I will close to not introducing him. So Professor D.D. Sharma is a professor at IISc in the Solid State and Structural Chemistry Department, and he have in the material science and at the border of physics and chemistry, and a lot of intuition from either directions, and have contributed a lot in the physics of related systems and nanomaterials. And for proper introduction, I'll refer to the 2021 Journal of Physical Chemistry tribute, which has a nice scientific account. And with that, I'll invite Professor Sharma for the talk. Yeah.
Do we have a pointer? Oh. Thank you. I better be down here because sometimes I get excited and may fall down. So it's ground state at the lowest potential energy is always safe. Thanks a lot for the kind, and thanks a lot to Professor Banerjee and everyone else who made it possible for me to be. I'm sort of embarrassed to admit that this is my first visit to IISc Tirupati. In my first visit to Tirupati itself, it has taken a long time, but the saying goes that when Balaji calls, you come. You don't come before and you don't come after. I'm really happy to be here, and it was wonderful. I mean, we moved in late in the night at about 30 in the night, and as we were wandering, both me and my wife, who's accompanying me, we really felt wonderful about this beautiful campus. It looked wonderful, large campus, space, beautiful buildings. I think it really excites the mind to do wonderful. Very happy to be here and interact with all the faculty members that I have been doing. What a colloquium is a mouthful of technical terms that many of you may not know anything about. You may not know what halide is, what a perovskite is. Materials is sort of an English term, but most of it otherwise would sound very to you. But I'll try to break it down and make it understandable as I go along, trying to be as simple as possible for all of you. Most of the work that I'll be talking about, today's talk is entirely based on our work and my group members' work, collaboratively with many, many groups. I'll go along, I'll introduce those groups also. And it's been funded rather generously by several agencies, and I'm very happy to acknowledge their contributions. For example, different arms of Science and Technology, ACRB, Nanomission, and Department of Science and Technology. A private funding agency, Jamshedji Tata Trust, at one stage for about 3 years, funded our activities very, very generously till about 2021, between 2018 and 2021. At present, all our activities are supported by this very, again, the very generous fellowship. It's called CSIR Bhatnagar Fellowship. That supports almost all our activities. And we also have some support from DST right now. Talk about today, of course, it will start with introduction to a class of compounds. Tell you what this class of compounds is, so that you can recognize them if you come across that at any other stages, any other context. And I'll tell you why we are excited about it. And we is a really large class of we. There are thousands of groups all over the world excited about it. And it has involved material scientists, chemists, physicists, come diverse background and diverse interests, because the class of materials that I talk about have shown extraordinarily promising properties and promising results, real possibilities of translation into application, revolutionize many, many fields. And I'll give you a flavor for many of these as I go along. And then I'll, after having told you about the excitement, I'll then focus down on something that talk about low dimensional systems, and I'll explain to you why one is motivated about the low dimensional. Basically, will open up the possibility in this class of compounds, infinity. The number of different things that you can explore will be huge, so that the properties you can explore would be really mind-bogglingly large, and that's why people have moved into the low dimensionals. We talked about that, and most of the applications and excitement that I'm talking about here, what we call the optoelectronic properties. What do I mean by that? It's basically the optical property and electronic property. A semiconductor, for example, the laser pointer, the laptop that is being used, all these are, or the projection that is happening right in this room, everything is are examples of optoelectronic properties of material being used. Our modern life is extraordinarily dependent on optical properties, and sometimes coupling of these two degrees of freedom. They're actually one and the same, these the electronic structure of materials. So optical properties and electronic properties are cross-coupled at times, and that's what most of the excitement about. But for the last part of the talk, are there interesting aspects of this class of compounds that I'm talking about, the optoelectronic properties? Because so much of optoelectronic properties is being talked about, thousands of groups working and many tens of thousands of papers being published. At times one begins to get and bored, saying that do I have to all the time only worry about optoelectronic properties? And I'll show you that there's life beyond optoelectronic properties. There are really interesting properties that people have not explored enough in this class of compound. So let me get started with introducing the compounds that I'm talking about. So the first technical term that I talked about is perovskite. Perovskite is the name of a class of compounds. It really tells you about a structure. And how do I think about the structure of the compound? The chemical formula of this particular structure is typically of this kind, ABX3. Three different ions will appear at A, B, and X site. These are cations, positively charged. X is typically negatively charged anion. Perovskites are normally, and that's why X is normally an oxygen. Three oxygen atoms, ions, and two metal ions together, whose net charge would then neutralize the charge of three oxygen ions, make the chemical formula. And you know many of them. Barium titanate is a well-known ferroelectric, and strontium titanate, the paraelectric system. These are classic examples of the perovskite structure. Perovskite structure has been the favorite playground of material scientists, condensed matter chemists, and physicists, because it's amenable to many different kind of modifications by applying pressure, applying temperature changes, making compositional variations, and deriving other structures that are related to perovskite structure. It gives rise to the high temperature superconductivity. The structure is related to perovskite structure, colossal magnetoresistance, also related to this kind of structure. So it's a fantastic structure, and people have been playing with it for the last 1 century at least. I told you that it's most of the time oxides, and perovskite structure, what does it look like? Just think of a cube. Take the cube and then place A, B, and X at the way that I'll explain to you now. For example, think of the A ion, put it at the center of this cube, body center position. Take the B ions and put them at the corners. And then the X ions, put them at the edge. These red dots you see, at every edge center I have put one red dot, and that's those X ions. And that will make the perovskite structure. It's as simple as that. It's a cubic structure, and you can now, this B ion is coordinated by 6 red dots, forming an octahedron. So it's a BO6 octahedron, and that somehow connected, and I'll show you how they're connected. But before I get there, let me explain the other technical term. I already told you it's normally oxide, but the subclass that I'm going to talk about, X is not going to be an oxygen ion, a halide ion, chlorine, bromine, or iodine. Since normally perovskites are oxides, I need to remind ourselves all the time that I'm going to talk about a halide perovskite. So the class of compound that we are talking about here are not just perovskites, but the special variety of perovskite, which is a halide perovskite. And then we also know that the A ion normally are a large cation, a metal ion like cesium, strontium, or lanthanum of some oxidation state. But the specific variety, the subclass I'm going to talk about, it's not going to be any of them. In fact, it's not going to be one metal ion, it's going to be an organic ion. It's an organic molecule like methyl ammonium with 1+ charge, formamidinium, this one. That entire organic molecule I'm going to put inside there. That makes it different from the traditional perovskite. I must remind myself by calling it hybrid because it is not only made of inorganic material, but I have put also an organic molecule inside. That's why we call it hybrid halide perovskite. The structured perovskite, the ligand ions are halide ions, and it's stabilized by this A occupied by an organic molecule. So it's a very peculiar one where both organic molecules are coexisting in the same structure. And then this, often I'll be calling this methyl ammonium as MA, methyl ammonium, or formamidinium. And the structure that I have talked about, as we have seen right now, all the B that I'll be talking about will be lead 2+. In some other cases further down, the copper. So these are the kind of compounds I'm going to talk about. Lead with one or the other halide ion, and at the A site, it could be Ma, Fa organic units or a cesium ion. The structure is simplified. This is the methyl ammonium ion that we have put over here. And now if I draw your attention to this atom in this structure here, in this structure here, you can see that this one belongs to this octahedron here, but this one also is common to this octahedron. This particular atom stitches these two octahedra together. Likewise, consider this one, which is here, it belongs to this octahedron, but it also belongs to this octahedron. Atom stitches this octahedron to that octahedron. Similarly, that one, if I look at, is this octahedron with that octahedron. And this stitching goes all the way along this line and along that line, forming a three-dimensional structure of corner-connected octahedron. So it's easy to think of the perovskite structure as this octahedron BO6 or BX6 octahedra, which are corner-connected in all 3 dimensions. That's what three-dimensional structure we are talking about. The reason we call it three-dimensional structure, looking only at the octahedron and not at this one, is because it is believed that the optical property and electronic property and magnetic property and mechanical property, whatever, are essentially controlled by this connectivity. This connectivity controls how the electrons move around, and since electronic properties eventually decide all properties of the material, properties are dictated by the way the electron can freely roam around direction, that direction, and that direction. So it's a three-dimensional structure. So remember that four-dimensional structure, where you'll find that this connectivity will be broken in a particular way to give rise to structures longer three-dimensional. And so having introduced that part, now I excitement. That was the structure. Why are we excited? It turns out that these compounds, as I've said, are really revolutionizing many different classes of application and fundamental studies. The 3 that have become very important is that these materials have turned out to be extraordinarily good detector material. They can detect energy particles of all varieties, but most focus is today about photon detection. Detect other high energy particles with great efficiency, and I'll show you some examples. There are also fantastic light emitting devices, and I'll show you some example of that. But most extraordinary application and the excitement started by realizing that there are spectacular photovoltaic properties. So you have energy generation and efficient energy utilization and very efficient energy detection out of the same class of materials. So everything that you can think about energy, it is relevant to that in one way or the other, this class of materials. What do I mean that They're spectacular in terms of they have exceptional efficiency. Depending on which one I'm talking about, I find different kind of efficiency, but the efficiency is extraordinarily good. So that makes it very attractive. Not only that, also extremely low cost material in both processing and raw material wise. Silicon photovoltaic. Photovoltaic, you know, today is a fantastic technology. It has made inroads, have silicon technology, delivering, creating power, converting solar energy at a rate which is competitive or even better than, cheaper than the traditional energy generation. And this is absolutely critical because our civilization produced using fossil fuel to generate energy and our fantastic dependence on energy is driving a precipice where we might fall off and the entire civilization could get annihilated simply because we do not know how far away from truly non-sustainability that we are driving ourselves to. And this is the reason it's environment and every aspect is getting affected, and photovoltaic is perceived as one of the. But if you think about it, and silicon photovoltaic till 5 years ago, it was not clear that the amount of energy I need to create one solar cell will give me back enough that I needed to make it. It's called energy auditing. Energy auditing is positive or negative was not clear even some years ago. It is extremely energy intensive process because it needs very high materials can be created with very low temperature, at low temperature by solution processing. And that gives rise to many other advantages. I'll not go into that, but just to make you feel the kind of advantages that this material class gives us, I wanted to mention this point. I'll give you one detection, one example from light emitting device, just to give you a flavor of it. And I'll spend a few slides to tell you about the photovoltaic to give you a more detailed understanding of its extraordinary problem. This is a classic paper in this class of compounds, which showed its fantastic or optical properties. CSPB-X3, X can be, as I told you, chlorine. Depending on which one you use, you can get different colors. And in fact, at X, you can have both chlorine and bromine simultaneously by saying that I'll have chlorine 1 and bromine 2, or bromine 2 and iodine 1, and making different composition. You can make any color. Basically, you make these nanoparticles, they themselves don't have any color, but if UV light on it, it down converts that UV light and gives out this brilliant light. It's brilliant. For every 100 photons that you give in, how many photons come out is the measure of quantum efficiency of any light emitting device. The light emitting devices that off normally are at best in the 30–40% efficiency. But these materials approach a quantum efficiency of 90%. And that's why here you can see the quantum efficiency is from 50 to 90%. And you can cover the entire visible spectrum, which means that you can combine them to have, you can have lighting and many other applications. And people are going ahead in very serious way in utilizing them. One slide to give you a flavor for the detectors. For example, you break your hand, a bone, you want to take an X-ray image. You want to have the image as possible for your doctor to know exactly where the fracture is, the nature of the fracture, so that it can be absolutely optimal. And you want to do that with the lowest amount of X-ray exposure. Of X-ray exposure, it's bad for you. So you want to have a detector image with the lowest amount of exposure to X-ray. The traditional X-ray photon detector is shown over here. This is in some units measuring the amount of X-ray I'm exposing. I'm trying to detect or image a pen. When I expose only this many X-ray photons, you see that I don't see at all any image of photons, and the detector cannot detect anything. I get up to about 200 or so, get nice, good images. Here also the clarity is not good. The traditional detector, but if I use CSPB-X3, then you can see that even at 29, you begin to see with much better clarity. So you can really reduce by almost an order of magnitude the photons that you need in order to get a clear-cut image and a high-resolution image with the diagnosis can be done. And a lot of activity. A few slides on photovoltaics. There's a very busy slide. It basically shows different technologies. We are using different technologies, developing different technologies in the laboratories to solar photovoltaic effect. And what it shows is how the cell efficiency is increasing with time. Different technologies, but let's focus on technology. And this is the multicrystalline, polycrystalline silicon technology. And there's the single crystalline. You can see that it started somewhere around 14% efficiency, and now it ended up here around 24% efficiency. And it took me 43 years here to there, a very slow increase from 14% to about 25, 26, nearly 50 years of development. And this slow development is absolutely critical for the fact that today's technology has really made inroads and making viable electricity production. The I mentioned to you has taken to start from the same 14%, only 7 years to grow up to more than 24%, 20% within 7 years. And you can see the spectacular rise of this, and that is very excited, and it has crossed the efficiency of silicon to see how this can be best used in making solar cell more efficient, and a lot of work is going on there. What makes it so good in the context of solar cell? It has nearby ideal band gap, because the band gap of a solar cell material has to be optimized. Why is that so? If the band gap is very large, of low energies will not be absorbed because it will pass through, because it cannot make the electron hole excitation, right? The photon energy has to be larger than, equal to or larger than the band gap. So the band gap has to be small. I can make the band gap very small so that every low energy photon, which is absolutely fine, I'll get a lot of current, but the voltage that I'll get from the device cannot be larger than the band gap. And what you want to maximize is not the current and not the voltage, but the power. Power is proportional to total energy that you're generating, which is voltage multiplied by the current. And that needs an optimal band gap such that voltage multiplied by current is maximized. That is approximately 1.4 electron volts. These materials that I'm talking about have band 1.5, 1.6 electron volt. So it happens to be having the right kind of band. It also has very low excitant binding energy. What do I mean by that? Excitant binding energy, when does photovoltaic effect happen? A photon comes of sufficient energy, it gets absorbed, electron jumps up to the conduction band. So you have a hole in the top of the valence band, electron at the bottom of the conduction band. Now these two being oppositely charged, electron being negatively charged, hole being positively charged, they attract each other. They attract each other by Coulomb interaction, and the initial energy with which they're attracting each other, or the binding energy of this positive charged particles, is called the excitant binding energy. Why is that important? Because two are bound very strongly, they will not become current, because you have to break them apart and take the electron in one electron and hole in the opposite electron. So you excitonic binding energy to be low compared to thermal energy. If it is much larger, much larger, more than 100 milli electron volts, it's not going to be useful. So the excitant binding energy needs to be. These materials have intrinsically low excitant binding energy. They have long carrier. Basically, you want the electron and hole to be able to travel long distances and go to the electrodes. You need, of course, the material must absorb. Everything is good, but if it absorbs no light for some, then also it's not going to help. So it must absorb light very efficiently. And finally, also, it must be defect tolerant. That's a technical part I'll not go into now. So everything sounds so good that one begins to wonder, and I've already said it's soluble, that there must be something not quite right? When everything's going good all the time, getting the maximum score in all the quizzes one after the other, you know that end sem will have some. And this particular compound has a very bad news in the end sem. When people started, when the end sem came, they figured out where the catch is. It was fantastic, have suitable band gap, low excitant binding energy and all that, but environmental stability. What do you mean by environmental stability? This material is fantastic within the first microsecond of its life. After that, I'm exaggerating a little, within an hour or two, it just degrades. You need a solar photovoltaic cell to be alive for 25 years. That's of the commercialization. And this degrades within hours. Within example, if you take this device, the material is black in color, coated on a glass slide, dipped in water, literally instantaneously turns into yellow, which is lead iodide. So the moisture in the environment kills it very, very quickly. This is a real trouble, and people are addressing this question. And this is the question that will take me to the question of exploring the low dimensionality. Before I say why low dimensionality we think about this particular trouble, let me tell you how we get to the low dimensionality. I've told you that this is my crystal structure, the perovskite. Magnesium, I can have methyl ammonium, or I can have formamidinium. But those are small ones. Now, organic molecules, there are thousands and thousands of organic molecules. And I can have many more which are not there. Organic chemists can make you any molecule, and they can keep making new molecules. But what to squeeze them in there? There's too little volume, space there, and they cannot get in. But if you bring in a molecule which has a tremendous affinity to hold hands with this inorganic unit, not room enough, what that will do, like a butyl ammonium instead of a methyl ammonium, because smaller and butyl group is much larger. Methyl ammonium would have been just this much. Butyl ammonium is this much. What it does is actually splits it open like this to accommodate the long length between. So it cuts here along this line, cuts. It's a two-dimensional connectivity. Now these octahedra are connected along this direction and perpendicular direction. In this direction, you see there's no connectivity. So this is now a two-dimensional structure, derived from the three-dimensional structure because I've put in this. Now I can play this game even more. I more quantity of these kind of things, and I can cut these also and make one-dimensional chain perpendicular, which are the other direction. Then I can cut in the third direction and make zero-dimensional structure, where the octahedra are all separated in all three directions. So the electronic properties are all confined zero-dimensional. That's how we make different structures. But why did you? Now you see, now that I have a huge library of organic molecules that I can now choose organic molecules that are very, very hydrophobic. They hate water. They repel water. And if I put such molecules here, will not allow water molecules to come near my inorganic part, which as soon as it sees moisture or a molecule disintegrates. So I will put hydrophobic molecules here, therefore make stable against moisture, because water molecule will not be able to come close to it. That is the idea with which we already started exploring low dimensional system. That also tells you not only that, now you have a huge possibility. You have the properties of this inorganic slab, and you can put whatever property you want of the organic slab, organic molecules, and then this will have the sum total of these properties plus these properties. You can ask a further refined question and say, well, that's a sum total, but do I have a effect? Can the property of this one start to influence the property of this one? Or the property of this one can influence the property of that one? And these are the questions that I'll be asking as I go along, showing you how that can be realized or where we fail to do so. This stability against moisture comes with this, because nothing comes free in life. One of the problems is that now your electronic structure is two-dimensional. Earlier, you had a three-dimensionally confined object where that electron and hole wave function could be delocalized in all three dimensions. Now it is only two-dimensionally confined, and that makes electron and hole get squeezed onto each other. They cannot separate each other as effectively as it would if it had more functionality available to it. And this squeezing together increases the Coulomb interaction between them. So the excitonic energy goes up. You can see that the excitonic energy of this kind of two-dimensional objects are in the order of hundreds of milli-electron volt, compared to the three-dimensional ones in the order of 30, 60, 70 milli-electron volt. So I gain the obesity or the environmental stability, but I lose the energy. Also, because of this very confinement, the band gap tends to increase from the optimal value. So as I'm going towards increasing environability, I'm losing the other two good attributes of small band gap and small excitant binding energy. And this led one of my students, the Parieri, an exceptional student. I've always been extremely fortunate to have very, very exceptional students. She is now doing a postdoc abroad. She is the one who asked this question: can I make a two-dimensional system derived from here, which will have a band as small as possible, and also the excitant binding energy will be small. She had some logic of thinking about it. I'll not go into the logic. I'll tell you the results that she found. Work was a collaborative work. The calculation that came from Filippo's group. Arup is now at IIT Hyderabad, a faculty member, a colleague at SENS Institute, Pralay Satra, and the photovoltaic work was done by a colleague at IIT Bombay, Shaival Sarkar. His student Arya Vidhan did that. Debashmita took and in our department, I very closely collaborated with my colleague Avishek Mandal and Professor Guru Rao, these faculty members in the department. She took a patent in the 2023 and published this paper in 2020. And you will get all the details there. This is the molecule she used. This molecule is too large to the cube, that body center position. So it splits open the cube, dimensional object. Beautiful crystals you can make. But the result, when material she took and looked at the band gap, here all the band gaps of such molecules, systems, two-dimensional halide materials, two different color coding. Do not worry about that because there are two different ways this can be done. But the band gaps are given here. You can see the lowest band gap is about 2.2 something. The material that Debauche made has a band gap here, which you can see is the smallest band gap. Even today, it holds of being the smallest band gap material in this class of compounds. So Debashmita wanted to understand this band gap. What is the structural aspect? Because eventually it is structural aspect that causes the electronic properties. And so what is the structural aspect? And she had some reason to suspect PBI-PB bond angle that is relevant. And so she plotted the band gap of all the literature, including her own, which is sitting over here. Here is the band gap as a function of the angle. And you can see that roughly speaking, as the PBI-PB angle approaches, which is the maximum it can be. Because if it tries to be more than 180 degrees, the other angle becomes smaller, right? So 180 degrees is the maximum angle that can be there. As it approaches, band gap roughly comes down. And there's a very good, easy way to understand that. Basically, is with 180 degrees angle, the electrons have the best probability of hopping to iodine to lead. And this ability to hop makes the bandwidth larger, which makes the band gap the smallest. And that's why you find the band gap the smallest. So with the model she chose, she managed to get no one else had got this 180 degrees magic angle. We also understand why that happens, but I'll not have time to go there today. But I'll point out and binding energy that I talked about. For that, she has to make a thin film sample and then various temperatures, the absorption curve. Absorption curves tells you how photon energy is being changed. The band gap is more than that. At this energy, it begins to absorb. This is the excitant forming signal, and this is the free electron hole forming signal. So that deconvolved or decomposed into an absorption coming from electron hole, as electron hole absorption, and the excitonic absorption. The difference between these two energetically is a measure for the excitant binding energy. There's a rigorous way of estimating it from there. Debashmita did that to find, as a function of temperature, what the excitant is. But what is relevant is about only 48 milli-electron volt at room temperature. Compared to other materials in this class, it's much lower. Once again, it is so much lower simply because the band gaps are much larger. That gives screening, and also the molecule that she had chosen was chosen to provide very good screening so that the Coulomb interaction gets screened. and lowers binding energy. And she indeed was able to do that. And also the water stability, which was the original motivating force. You can see if she takes MaPbI3, the three-dimensional object is instantaneously comes through lead iodide. Here you can dip it there for hours together, nothing happens. In fact, test of it by looking at the photoluminescence before putting it in water and after, and superposing them one on top of the other, and you see absolutely no effect. So it's extremely well preserved when dipped into water. So they have very good stability. And we also looked at the photovoltaic. The conclusion for this part, I'll just through it since I've already told you about it. I'll not talk about the photovoltaic stability issue, but take you to the exploration of lower dimensional system. In this lower dimensional system, one can go, we have looked at 2D, but there can be zero-dimensional, one-dimensional system. Aiming for a zero-dimensional system with the motivation that I've already seeded in your mind when I said, can I have the organic molecules properties imprinted on the inorganic part in some way? And this is a very interesting question because I can choose an organic molecule which is chiral. And chiral molecule, it's like hand. My right hand, they're mirror image of each other, but there's no way if I try to put them on, I can do that. My thumbs are going in different direction. There's no way, they're not identical, they're just mirror image of each other. And this is called chirality. And chirality, of course, plays very important role. Chirality is important for life itself, as you well-defined chirality. And it reflects itself in many different ways. Our interest was more electronic and optical properties of chiral system. So a student of mine, Ranjan Das, who drove this, did I not use their name? It will come in a moment, chose this chiral molecule. And this actually, there's another work, this was not 1999, which showed that if you take a chiral system, chiral molecule, and make electrons interact, electron of upspin and downspin scattered differently. Basically, chiral molecule spin filter. It filters the upspin and downspin differently. So to talk about it in terms of cartoons, which is the picture I've borrowed from this paper recently, that if you take a chiral molecule, like a coil of a spring, one particular spin direction will go through, but the other spin direction will go through. So you start with both kind of spin, but on this side, you'll get only one kind of spin. So it's a spin filter. And then if you reverse the chirality, the situation gets reversed. And this, by taking, they said, this is what they're going to do in this paper. They took the same molecule, intercalated it in tantalum disulfide, which is a two-dimensional crystal. There's van der Waals gap, and you can squeeze in these molecules here. And once you squeeze in only one chiral molecule, the system would be chiral, because chirality cannot be averaged. Even if it is randomly going, it will be chiral. And so they made that system, and then they looked at the optical property. The way you detect chirality is by doing absorption experiment twice on the same material. Once you do the absorption experiment with right circularly polarized light, and the other time you do it with left circularly polarized light, because right and left polarized light absorb differently depending on whether they're in sync with chirality of the molecule, out of sync. So immediately the difference between the two, if it is a chiral system, if it is not a chiral system, both right and left circularly polarized light absorption will be identical, and you get zero in the difference. So we are plotting the difference here, which is called the CD, as a function of the photon energy that I come in with left and right circularly polarized light, and the difference is what I am plotting. You can see there is no chirality in the electronic states here in energy, but there's a lot of chirality here because it's non-zero. If I have only tantalum, that's non-zero everywhere. But here it becomes chiral. If I reverse the molecule, this signal reverses itself, showing the system is chiral. Good. Then one asks, is it chiral only at this part and not at that part? That part also is tantalum disulfide absorbs there. It has electronic states. And it has electronic states way down, only very high energy states are chiral. Why is that? Then, and when we ask the question that this chirality that you're seeing here actually is because of absorption from these molecules. These have their electronic states here. The inorganic part has not only electronic states here, but also here, and there's absolutely no chirality transfer. So the question, can we have chirality transferred? What are the design principles? What do I need to do to have transferred from the organic molecule to the inorganic molecule to make it chiral? And this is a question that my student Ranjan, this very spectacular student, who is again doing his postdoc right now abroad, asked the question, and again Filippo's group and Pralay's group contributed. And what Ranjan showed in this paper, he worked with the same molecule. It has absorption exactly in this part of the wavelength that I told you about. It has a strong CD signal, only the molecule. He combines this with copper bromide. It's a new compound called MBA2. This is a chiral molecule, together with copper bromide, CuB4. And you can see that the organic molecule has no absorption above 280 or so. And this scale begins from where this ends, 350. You see huge chirality. This is a CD signal. Huge chirality transferred. These are states coming from bromide. So copper bromide becomes hugely chiral, which it was not. It is normally not. And so the chirality could be transferred from here to there. And the reason, and in fact, it turns out that it is the record high chirality in this orange red part of the spectrum in this class of compounds so far. This still holds that record. And this is because the system is zero-dimensional. What do I mean? If you look at the system, the crystal structure, you find copper, bromide, copper. You see this bromine is not shared with the bromine of the other one. All four bromine, this copper has its own unique bromine. In the other structure, three-dimensional structure, this bromine would have been this bromine. These two would have been stitched together. As soon as you have structure stitched together, you can see chirality, which is a statement of rotation, is going to be difficult, because now think of that you have one copper bromine like this and bromine like this. If I have them not connected, I can rotate them like this. No problem. Connected, when I rotate this one this way, the other one rotates in the opposite direction. So this one rotates that way, that one is rotating this way, because this is a common bromine. So by making it zero, flexibility of rotating them the way I want, and that's the reason it shows that the molecule here is able to rotate this one the way it wants, because it's zero-dimensional. There is this to this story that I'll not have time to go into, but it also has a quasi-dimensional structure. Basically, this is the level at which this strict dimensionality that I talked about gets blurred. But for that, I refer you to the original paper. It'll get technical, but I'll leave it at that point. Just mentioning that if instead of bromine, you take chlorine, a twist comes into the picture. The twist is the system is still chiral. This part also becomes chiral, but the system also becomes ferroelectric. Ferroelectricity has the ability to discriminate between positive charge and negative charge, because it has a polarity built inside. And the chirality has the ability to discriminate between upspin and downspin. An electron has 2 degrees of freedom, the charge and the spin. So if chiral one was able to discriminate up and down, now you've the ability to both up and down and electron and hole. So you have the 2 degrees of cross-coupled in this class of compounds. But I'll not go into the details of that. But again, driven by Ranjan group, and this was published last year. And if you're interested, you can look at that. So now I'll go to the point that everything that I've talked about so far is optical, electronic, optoelectronic, depending on how I want to use it. Basically, everything is connected to electronic structure. Is there anything interesting about these materials if I stop thinking? And I paraphrase that in this question, is the life, meaning interesting life beyond optoelectronic properties? And I go back to additional 3D, three-dimensional system. And I'll take two examples in quickly to tell you and ask the question that is there any way lower the value of a physical property below its minimum value? Now, that's an oxymoron. Minimum value is defined by the value that you cannot go below. And the statement I'm making is have value lower than the minimum value. And I'll show you by a twist of language, indeed it's possible to get to a value of a physical property lower than what you thought minimum value should be. Okay. And the second one, allow me with my Bengali somewhere lurking still inside after 50 years of being away from Bengal, that I would love to know fish is fresh. And how do I do that? These are the two examples that I would like to talk. Let me first take this one. And this, again, driven by Debashmita, very closely collaborating with student of Kanishka, Parivesh, and student of Umesh, Arijit. These three conspired together to do a beautiful piece of work. It also was very well supported by my colleague, Arindam, and his group members. This paper was published last year in this particular journal. Going to look at is thermal conductivity. As you know, thermal conductivity is carried by phonons and electrons, but these are, I told you, band gap of 1.5, 1.6 electron volt, which means electronic degree of freedom is not there. At room temperature, there are no electrons to carry that heat across. So only phonons must carry the heat. So there's nothing electronic about it. So thermal conductivity is a property that has nothing to do with electronic structure. And that's what we are going to look at. When you're looking at, and this was already known, the thermal conductivity of this compound was usually low. In some units, it's 0.34. This was known. It's not our discovery. Now, it's unusually low. So Debashmita asked the question, how low is low? Everybody's saying it's very low, ultra low. How low is low? So she went and asked the question and said that how low can the thermal conductivity of a crystalline solid be, or a solid be? Phonons are going to carry the heat. Phonons are, as you know, atomic vibrations, coherent vibrations of atom through the lattice. And if these, while they're carrying the heat, get scattered, the information will not get carried. So if the phonons, the heat-carrying acoustic phonons get scattered very much, thermal conductivity will go down. And if the heat-carrying capacity or the phonons are very fast and going very beautifully without being scattered, the thermal conductivity would be large. So the question is, how efficiently can I scatter? If I want low thermal conductivity, how efficiently can I scatter the? Now, in the limit, how efficiently can I do? The smallest mean of basically mean-free path is the distance over which it goes before it gets scattered. If the mean-free path is very large, I'll have thermal conductivity. I want to make the mean-free path smaller and smaller and smaller and smaller. What is the smallest distance that I can think of to scatter a phonon? It cannot be smaller than interatomic distance, because it has to be another atom that scatters the phonon. So the smallest path length of mean-free path of phonon can be the interatomic distance. So if I have a glassy system, that means there is absolutely no periodicity. Then the mean-free path, which actually gives me the thermal conductivity in terms of specific heat, speed, sound velocity, and the mean-free path, the smallest value of mean-free path can be the interatomic distance. It is the minimum conductivity or minimum electronic conductivity. It's called the Ioffe-Regel limit of conductivity. And this was worked out by Cahill, and that gave us the number, what the value should be, this minimum thermal conductivity, when the thermal conductivity is such that the phonons are separated by interatomic separations. The maximum, this is the lowest thermal conductivity. So with that Ioffe-Regel limit in mind, and this was known, Schmidt asked this question. Strangely enough, nobody had asked that question before. And that's why I put this red line. Everything that I'm going to tell you after was not known, and Debashmita discovered them. That activity within this limit is 0.51. And so there you are. I had promised you that here is a thermal conductivity that's lower than the minimum value. And that happened. It just cannot happen. I mean, we are talking about, this is glass limit. Is this material glassy at all? I mean, if you look at its extra diffraction, it has such sharp, there's nothing glassy about it. And yet the thermal conductivity is lower than, saying that there's absolutely nothing ordered about this material. This happened. And what is this value? Where is this coming from? Not this one, this even 40% lower than that. So that's when Devashmita looked around a little more and asked the question, but not solids, but gas also carries heat. It does it, the thermal conduction is by convection, by imparting kinetic energy, by diffusive of the atoms. So if I don't have any phonons in the system, if my atoms are ordered that they are imparting the kinetic energy only by diffusive motion to each other, like it would happen in a gas, what would be the limiting value? And that is, this paper had worked out in 2018, and the limiting value, in the diffusive model is given by this. And so Devashmita went ahead and calculated and found that exactly equal to that. So this material is at the diffusive limit. But the problem is that it's in a solid. What is making it diffusive when it comes to thermal conductivity? And then she thought that, well, there's something peculiar. This character here, we have not thinking about. Remember, optoelectronic properties are all controlled by this lead and iodine network. This character, what is it doing? And this is a question that people have been asking, and we have been asking for a very long time. Originally, people had thought it has a large dipole moment and it will make the system ferroelectric. It's another student, many generations before, Sharda in our group, had asked the question and had shown that actually this molecule is rotating very fast. And I'll jump through because I'll not have time to go through all the details. From dielectric spectroscopy, she had shown materials are rotating very, very fast. That's a paper in 2017 that Sharda published. And she showed collaborative work with the Vienna group that they're rotating at a timescale of 6 picosecond. And this picosecond timescale is the timescale of the phonons. So this rotating dipole, which has nothing to do with phonons, completely localized motion, scatters the phonons so rapidly that it's complete of phonons, and for the thermal conductivity, you recover the diffusive limit. So it comes to a diffusive limit. And indeed enough, when you do the, which cannot describe this full rotation, but talks about the incipient rotational modes, we find indeed that the yellow phonons, this gets technical, I'll skip that, but basically there are signatures in the phonon calculation that indeed these rotational motions of the MA are scattering the phonons very, very strongly, giving rise to tremendous amount of anharmonicity, which is essentially means that the lifetime of the phonons are very, very short. Phonons don't live to be phonons for long enough. And that's why thermal conductivity is so low. But what happens if I dope Fa in this? See, I can dope Ma and dope Fa. Fa also will rotate. And then a funny thing happens. The fun if you make a solid solution MAFA, you would expect physical properties to evolve linearly. That's called Vegard's law. For example, lattice parameter, you can see of this MAFA composition is changing almost linearly. This one I leave out because there's a chain crystal structure here. Lattice parameter evolves linearly. Band gap evolves linearly with fraction. But the thermal conductivity goes completely, has a non-monotonic behavior. And there's again a puzzle that is very difficult. And not only that, this was already at the diffusive limit. And am I going below the diffusive limit then? And there's no model to do that. So then Devashmita said, let's diffusive limit for each of these compositions. It turns out that life was saved at that point. We found that the diffusive limit of these materials is plotted here. So essentially for these compositions up to 0.3 Fa, 70% Ma, it comes down, but that's because diffusive limit itself comes down. That for some reason the thermal conductivity begins to increase with respect to diffusive limit, showing that Fa, when I'm going to Fa rich end, Fa is not being able to phonons as well. It's only Ma that scatters very well, but in the beginning, somehow, the presence of Fa makes the phonon scattering improve. I'll give you there's a huge amount of work that you have done and many years over with small angle neutron scattering, etc. There's some very peculiar thing there. As you're doping Fa, first of all, why Fa is not able to scatter so much high to Fa? Diffusive limit is here, but the actual value is up there. Fa has a dipole moment. Fa is rotating as much, but Fa has a dipole moment which is 1/10 of Ma. And it is a dipole moment on Ma that scatters the phonon, allows it to interact so well with ionic lattice that is vibrating. When the dipole moment is low, though it's rotating, but the low dipole doesn't scatter the phonon so efficiently. So Fa is in scattering, and that's why it's coming up. But what makes it come down in the beginning? Fa size is slightly larger than Ma. In this limit, Fa, the average volume is increasing, and that allows the Ma to rotate even faster. And you have seen, actually, we had not known about this. We had already published 4 or 5 years before from small angle neutron, showing that Ma actually begins to rotate faster in the small doping of Fa limit. So it indeed rotates faster as the volume increase, and that allows it to bring down, but volume increase does not compensate for decrease of Ma ions. So the number of dipoles are going down, and so it begins to go up. So that's the story. If I may get 5 minutes, is that okay to tell? Otherwise, fish will. Okay, fine. So I've told you about going to spend time on it. Let's get to the fishy business. So how do you know that your fish is fresh? Well, if I had told you that what I'm going to talk about is evidence thermal metastable phase in a halide perovskite, optically tracked thermal breach memory, I'm sure I would have. So it was a trick to tell you how to keep the fish fresh to keep you here. This, even for me, would have put me to sleep even before it started. But truly, what I'm saying, the translation of this in a Bengali English is how do you know your fish is? And let me tell you this in a few minutes. This is a wonderful collaborative work driven or ISAR Kolkata, Bhavtosh group, and these two are from ISAR Kolkata, from our group. They're equal contribution first authors. It's a wonderful work, just appeared, I think, last week in this particular journal. The first observation was that photoluminescence. I told you these give out colors, light, beautiful. So we are going to look at the photoluminescence, and these materials also have a first order phase transition. At room temperature, 300 Kelvin, it's in diagonal phase. At low temperature, below 160 Kelvin, it has an orthorhombic phase. It's a first order, there's a hysteresis associated with that. And we were trying to follow this phase transition, photoluminescence intensity and the shape. So we are going to cycle through. We'll start with 144, we'll heat, go to 158, heat, go to 170. Then we'll start to cool, come back to 158, the same temperature, cool further 140. You see that when I cycle through 144 heating or cooling, they're exactly of each other. The two spectra are exactly at the same place, because it's below the hysteresis of the phase transition. If I look at 170 Kelvin, which is above, these two are also exactly on top of each other. But when I'm inside the hysteretic region, 158 Kelvin, you see the two spectra depend very drastically on whether I came heating or cooling. Now, when I'm saying identical or different, identify how identical or how different, and there's a way of with what you call the Pearson correlation function. And okay, before that, I can just take the area, and if I plot, you see clearly the hysteresis of the phase transition. Also, so this point and that point are different. That is saying these two are different. This point they're same, at that point they're same. Now, to define how same or how different they are, this particular quantity with the two photoluminescence that we want to compare, two spectra. If it is identical, the value will be 1. If their value will be less than 1. Lower than 1, the farther away from 1 is more dissimilar there. Now, what we are going to do is play around with the heating and that I talked about. So always you'll find a little inset that tells you what I am doing with my fish. The fish starts at initially. I cool the fish down. At this point, I'm inside the hysteretic region. I start to heat up the fish, and then I'm going to hold the fish at the same temperature forever. So I start from here. I cooled it down. That is following this, I come here. Then I heat it up a little, add the photoluminescence in. I heat it up, went there. And at this point, when I hold and I keep measuring, all the photoluminescence spectra are one on top of the other. I have up to 14 hours all plotted here. You cannot see the difference. In fact, if I plot this Pearson correlation function, you can see that it's 1 within an error of 10 to the power minus 5. It holds on to that particular optical signal as long as it temperature exactly forever. It remains identical. Okay, so you can see that that doesn't vary, which is wonderful. And I can do that either that way, or I can do the reverse. I start from the low temperature, heat up, come here, then down, go there, and I hold it there, and it remains there forever. You can see thousands of spectra taken, and it's all within an accuracy of 10 to the power minus 5 of being identical with each other. Now I'm going to do further tricks. What I'm going to do is what I talked about. Yeah, so let's go there, sorry. So I'm going to start from low temperature, heat it up, and cool it down and hold it at a temperature which is hysteresis. This is the temperature at which I want my fish to remain. And this fish remained at that temperature, but somewhere in between it got heated up. And the transporter saw that ice had melted, came to my home. Before coming to my home, it put in the ice and brought the temperature down. I'm going to measure the spectrum. I sent it here. And when it gets delivered at home, I'm going to measure the spectrum here. Show you that though he brings the temperature to the same place, these two spectra would be different depending on it went up or went down. First, if it went down, then what happens? You can see if first it went up, nothing happened. Loop. This is the heating up, come here, cooling down, go there, measure this here. Then it went up, came down, so went up and came down. The spectra looks identical to what it was because I heated up. But if I do the reverse one, so the Pearson correlation function remains the same, how much the spike is, but it remains the same. If this spike is in the same direction, I prepared my thermal history. If the spike is in the reverse direction of the thermal history, immediately you see is different from that spectrum. And Pearson correlation function immediately deviates from 1 drastically. And though the temperature was brought back less than 2 Kelvin, even 1 Kelvin difference, I can pick out. That at some point of time, I don't know for how long, but the temperature had fluctuated by 1 Kelvin down and came back to the same temperature. If I'm going the other direction, I'll simply prepare the sample in the other way. That is, I'll come from high temperature, low down, and then it will be sensitive to this. So depending on which way, whether I'm interested in the positive or negative spike to be detected, I prepare the initial state different. Why does it happen? It happens all because of structure. The orthorhombic structure is given here and the tetragonal structure is given here. This one appearing at this angle and this one appearing at this angle. They're at 2 different angles. I'm going to take this part and expand it and show you. At 110 Kelvin, both cooling and heating curves, this are orthorhombic peak. Heating and cooling temperature, both are tetragonal, one on top of the other. But temperature depends on heating or cooling. This is the orthorhombic peak, and this is the tetragonal. Intensity is completely different depending on which path I came by. And since the photoluminescence signal of this phase and that phase are different, depending on the history, the photoluminescence intensity. And that's why I can know the history, though cheat me by bringing the temperature back, but it leaves an indelible mark on the photoluminescent signal for me to detect that actually there was a breach that you had broken out. And that can be all the experiment that I showed you with photoluminescence can be reproduced with X-ray diffraction. I'll not go through that. I already told you about this, and the time is over. Let me end my talk with that and saying thank you for your attention. Thank you very much.